All right, so I'm gonna go ahead and get started in just a second. Is everybody ready? Okay, so first, how many of you actually downloaded the source code for Uinta? Anybody? Okay, a couple people. So I'm going to be pulling up some actual code, so it would be useful for you to do that. So let me just point you to where you can find the command in case you don't have the email. So if you go to charlesmartinreed.com and you click on this scientific computing workshop, then the third workshop will have the svn checkout command to do that. And then there's also links to the user's guide and everything else there. Okay.
Fix my SVN.
Okay, so I just want to give you, so I'm going to start by talking about the Uinta framework. So you can see part 1 is going to be on the Uinta framework. And then part 2 I'm going to cover Arches itself. And so to understand Arches, you have to understand the framework. So the way the framework works is it's sort of this pluggable thing that just sits on a cluster and it runs. So when I want to run an Arches simulation, I have to run the Uinta computational framework. And the framework then runs Arches. So the framework kind of wraps Arches, and what the framework does is it provides me with some tools like parallelization. So it takes care of how to run on all these different nodes, and I don't have to know about MPI. I just run the framework, and the framework takes care of that for me. So using a framework like this, you can abstract a lot of the details. And then Arches just plugs in on top of that. So Arches is a component inside this framework. And so Arches communicates with the framework using special framework-related objects. And then the framework does the parallelization and the actual running. Okay, and then there's also a couple of other components in the Uinta framework. There's one called ICE, there's one called NPM, so there's several different components. And Arches is just one of those. So the UCF, so when I say UCF, that just means Uinta Computational Framework. The UCF is a computational framework. So what does that mean? Well, a framework provides you with common code. So somebody writing a component for solving incompressible or the inviscid Eulerian equations could use the same code as a large eddy simulation for viscous flows, and they could use the same equations, the same code as somebody solving, a porous media flow or something completely different. So it's this idea of using common code, providing common code. There's also generic functionality. So any kind of component that's built into this framework is going to need to save data to a disk, or run on multiple processors, or create common things like grids, variables, these sort of things. And so the framework provides this common functionality. So it provides functions for people building components that are common to a lot of different applications. And reusable abstractions, that's sort of the same idea. It's providing these abstractions for things like parallelization and data input and output, so that users don't have to deal with these low-level programming details, like how do I use fopen and dump my simulation data to a file. The user doesn't have to worry about that. They use these higher-level abstractions. And it's part of what's called an API, an application programming interface. So this is this glue here between Arches and the UCF. That connection, where the two connect, that's the API. And so this is really similar to libraries. If you stuck around for the end of the presentation last workshop, we talked about libraries. And so what libraries do is they provide the user with these chunks of code that they can use as part of their program. And so frameworks are really similar in that sense. Okay, so the UCF in particular is a computational framework. It's designed to solve PDEs in time. So anything of the form partial of phi with respect to t. So anything in that form, the UCF is designed to solve that. It's written in object-oriented C++, and the abstraction for parallelization allows you to parallelize to thousands of processors. Okay, so I'll just talk about the design now. So there's a way of designing a framework where you can use something called the common component architecture. And so different codes use this common component architecture. I believe Dr. Dev's code uses this as well. And so it's basically a way of designing components that can be plugged in. And these components have to have common features in order to do this. So every component has to define a certain set of methods. So every component has to have a way of computing a stable time step. Every component has to have a method to initialize the variables it needs. Every component has to, be able to advance the solution in time, and these sort of things. And in this particular case for the UCF, it's used to solve these time-dependent PDEs on a Cartesian structured mesh. So this doesn't handle unstructured grids. It doesn't handle radial coordinates or cylindrical coordinates or things like that. Okay, so for the framework, what I said earlier was that this framework sits on the cluster and it's the one actually running the code. So it's the one parallelizing and managing and starting components and doing all this work. And whenever you design a C++ program, you have to have a main function. No matter how big it is, no matter how complex it is, there has to be a main function somewhere. And that's located in this standalone Uinta simulation file, sus. Okay? So sus is the main driver, and if you open up sus.cc, you'll see a lot of messy stuff, but there is a main function there. Okay? So you can kind of think of this in this way, using this diagram. So the user provides some specifications through an input file. And that input file is read in by sus. So sus knows, okay, what component do you want to use? What grid size do you want to use? And some basic information like that. Then it knows where to pass that information. So there's all kinds of things like schedulers, MPI managers, task managers, and I'll get into some of those details in a little bit. But sus is the brains of the operation. It knows where to pass the information to get it dealt with correctly. And then it also creates a place where you can save your simulation data. And there's an abstraction for doing that so that you don't have to worry about file input and output. Okay? So the framework provides a whole bunch of things. There's just sort of a list that I just threw up there. It provides some things like Cartesian grids and patches and cells and these sort of CFD type of things. Things you'd want for solving PDEs of the partial with respect to t type. It also provides some variables, different variable types. It provides a data warehouse. So this is the input-output abstraction that I was talking about, where you store your data. It provides some other things like tasks and schedulers. That's how it manages all these different things it has to do. And that's how it achieves parallelization. So we can kind of divide these into different chunks. So we've got domain or mesh abstractions. So that these are things that the framework provides related to a grid or a mesh. So you can create grids, you can say I want a grid of this size, 1 meter cubed maybe, with this many cells. Maybe I want 50 cells in each direction. And if you want, there's also the capability to do AMR. So the code provides this concept of levels. So you can use multiple levels to do automatic mesh refinement. So these are sort of the domain level abstractions. There's also data abstractions. So these are, how your data is dealt with. So you've got variables, variable types. You've also got variable labels. So each variable that you deal with has to have a label. It's like a unique identifier or a unique tag. And you use that to deal with your variables. And that way you don't have to deal with, strings or, what's the name of that variable? I can't remember, or, if you define a variable in one class, well, now you have to share it with another class. So this variable labels takes care of all that messiness, okay? And then, finally the data warehouse, which I mentioned. This is for data storage and retrieval. And then there's parallelization abstractions. So this is how the UCF achieves this massive parallelization. So anytime you want to run a code in parallel, if you're running it in parallel on more than, say, 32 processors or good-sized processors, you have to have some way of distributing the work and identifying how much work is involved with each computation you do, so that you can distribute the workload, as opposed to having one processor trying to do everything and 10 other processors sitting idle and not doing anything. Okay. So I'll talk a little bit about the domain and mesh abstractions first. So the input file is where the user specifies all this stuff. They say, here's the domain size I want, here's the number of grid cells I want, here's the number of patches I want. And a patch is just a chunk of the grid that's owned by one processor or by a group of processors. So in the case of arches, the number of patches has to be equal to the number of processors. So this is like saying each processor is going to own a certain number of cells that are all going to be grouped together. And whenever let's say you want to do a forward Euler to solve this time-evolving PDE. So you have to calculate the right-hand side. So each processor is going to calculate the right-hand side, and they're all going to perform the same computations, but they're going to be doing that with different data, because they all own different data. So they're running the same task, but on different data. And that's the idea behind patches. So this is just kind of a schematic representation of what I was just saying. You've got some domain here. This is just a really simple diagram for 4 processors. So we're just going to split this up into 4 patches, and each processor owns a patch. So each processor is going to calculate a right-hand side at each of these grid cells, and each processor is going to do the forward Euler update on each of those grid cells, and so on. And processor 1 only knows about this patch. And when it needs to know something about a neighboring patch, for example, if we're discretizing if we're looking at a spatial derivative, then we need to know something about neighbor cells. So some information is communicated across patches, but only along that boundary and only as needed. So in general, one patch should not know about another patch. Okay? So next I'll talk about data abstractions. You can think of the data warehouse as a library. So when you go to the library and you want to, okay, so let me start here. So the data warehouse you can think of as a library. It's this repository of information, and it's all organized, it's all structured, it's easy to find things. If you don't know where to find something, you ask a librarian. So this is kind of what the framework does. It provides this method of figuring out where something is or retrieving something. So you don't have to understand, what each of these books are about and where they go. All you have to do is say, I need this book. And the librarian says, okay, you can find it on this shelf at this location. Okay, so similarly, each of our variables is like a book. There's a particular location for it, and this data warehouse manager understands where all the variables are kept. And if you need a variable, if you need the value of a variable, it knows where to find it. Okay, and so each book in here has a call number, and that's how you retrieve it. You say, I want this book. Okay, here's its call number, and then using that call number, you can get that book. So similarly, when you create a var label, this is a variable label. The variable labels I talked about. These variable labels are like the call numbers. They're like the unique identifiers that you're going to use whenever you need to get that data. So if you're doing a forward Euler and you're calculating the right-hand side and you need temperature, then temperature will have a unique variable label associated with it. And all you have to do is ask the data warehouse for that data and give it that var label, and the data warehouse will return that data to you. And so there's also this further analogy. You can carry this analogy further. If you walk into the library and you just pull a book off the shelf and walk out with it, that's not allowed. If that were allowed, then who knows where all these books would go. These books would be all over the place. They'd be unorganized. The librarian wouldn't be able to find the books. So when you want to, and similarly, you can't carry in a book off the street and just stick it in the bookshelf somewhere. So there's a similar analogy here. You can't just stick any data you want into the data warehouse, and you can't just grab data without asking for it from the data warehouse. So this is the whole ability. So this is directly related to the ability to parallelize. If you're running on 1,000 processors, and all 1,000 processors are trying to grab data, and they're not going through the data warehouse manager, it's like having 1,000 people trying to all get in a coffee shop, all at the same time, and everybody's just cramming in, and it's just chaos. But if they all go through a manager, it's like everybody forming a line and going in one at a time. Okay. Okay. So I'll just say a couple words about the parallelization abstraction. So each component has a set of tasks, and you can imagine, like I'm giving this example of solving a PDE in time using forward Euler. So one task might be calculating a right-hand side. Another task might be doing your explicit update. So any computation can be sort of split up into tasks. And any task is going to have things that it requires. So the right-hand side might require temperature, and it's going to have things it calculates. So you're going to calculate the right-hand side, or you're going to calculate phi in this case, if you're solving d phi dt. So each task has to specify what it needs to do its calculation and what it's actually calculating. And in that way, the data warehouse, so this information is communicated to the data warehouse so that when it comes time to actually do the computation, that processor sitting on that patch has all the data it needs to do its computation. And so the idea is that if the task manager, so if there's some manager of all these different computational tasks, if there's some manager that knows what everybody needs and when everybody needs it, then it can balance this workload and make sure that all of the work is distributed properly. Okay, so let me give just a little more concrete example. So let's say we're solving a species continuity equation. And to do this, and so this is exactly the type of problem that the UCF is designed to solve. This is a PDE in time. Okay, so let's say we've already calculated our convection term, and now it's just a matter of calculating the diffusive flux on the right-hand side. So this diffusive flux, to calculate this, we need del.j, where j is our diffusive flux. Okay, and j is going to depend on maybe density and the diffusivity. and the gradient of the concentrations. And maybe diffusivity depends on temperature and concentrations. So this is just one example of what our model might look like. Okay, so how might this be divided into tasks? Yeah.
The operators, you got them wrong in the tree. The first one should be divergence and the second one should be gradient. I think you have them in the other.
Yeah. Yeah. So it should be del W instead of del dot.
Yeah.
Okay. So let's say we had it right. How would we do this? Anybody have any ideas? Just give up. How would you split this into tasks? So what might be one or a task or several tasks? What might a task look like given this calculation?
Calculate the gradient.
Okay. So one task might be this circle here, calculating the gradient of the concentrations. Okay. What else might be a task?
Calculate temperature.
Yeah, calculate temperature. Okay. So maybe each of these little bubbles is a task. Or maybe if this is really simple to code, we just want to make this whole thing a task. Or maybe if the gradient operation is easy to do, but calculating the diffusive flux is not easy to do, maybe we want to make this. Maybe we want to make just this J bubble and everything below it into one task, and then the del dot J into another task. Okay, so we can divide this one computation up however we'd like. And so we can define tasks to be one bubble or several bubbles or even the entire computation. Okay. So the task graph takes all of these different things we have to do. So this is just a figure that's in the Umento documentation. So there's all these different things that you might have to do. And there's all these connections that you need. One task has to be done before another task. So there's this order of tasks. And that order is determined by, say, the value of one variable depending on another variable. And so that's done through this requires, so we specify what variables we require to do a computation and what variables we compute. So if I require a variable, then it has to be computed by something else first. And so, yeah, so each of these tasks is running on a separate processor, and each of those processors owns a certain portion of the grid, and that's their patch. And so each task has two data warehouses. There's an old data warehouse for the previous time step, and there's a new data warehouse for the current time step. So you can think of, you can think of this tree. If we want the density, if nothing's calculated the density yet, we can use the density from the previous time step or from the old data warehouse. Or if something's already calculated the density, then we can use the density from the new data warehouse. Okay. So just to sort of show these examples in action, there's some examples in the tree. So if any of you have checked out the code, then you can open up these examples and follow along. Okay, so I'm just going to go to Source, CCA, Components, Examples. And CCA stands for Common Component Architecture. Okay. So there's a couple of examples. The one I want to look at is this Poisson example. So let's look at Poisson1.cc. Okay, so the first thing you're going to see is some variable labels being created. So in order to use a variable, the first thing that any class has to do is to create a variable label for it. Okay. So I want to focus on two important functions in here. One is schedule time advance, and the other is time advance. So we saw with this abstraction that it's important to, before we do a computation, to explicitly say what that computation needs and what that computation computes. And so any method that actually does computations should have an associated scheduler. So the scheduler is basically going to say, I require this and I compute this. Or I require, whatever variables it requires. It explicitly says I require these variables, and whatever variables it computes, it says I compute these variables. And so the task manager says, okay, this task requires these variables and computes these variables, and it makes sure that all the tasks can be done in order, and that one task isn't trying to request a variable before it's ever computed, and this sort of thing. And then the actual time advance method is, where the business happens. This is where the actual time advancement happens. So this is just a simple Poisson solver, solving a Poisson equation. So let's look at the schedule time advance method. Okay, so we're creating a task here. Oops. So we create this task, and the task is time advance. And we say this task requires our phi at our old time step, and it computes phi at the new time step, and it also computes a residual variable. So when we do this Poisson solve, we're going to get a residual for each iteration. And then we add the task to the scheduler. So we're passed in some scheduler. So we don't know much about that scheduler. It's just sort of given to us. And then we add a task to that scheduler. So in the end, this scheduler is going to have a group of tasks, and each of those tasks are going to require things and compute things. And so the scheduler can organize those tasks and distribute the workload. Okay, so now let's look at the time advance method. Okay. Okay, so the first thing you see is we're passed in these data warehouses. This old data warehouse and new data warehouse. So this is what I mentioned earlier about this abstraction. We have a data warehouse for the old time step and a data warehouse for the new time step. And we're looping over all patches. So each patch is doing something. So in other words, we're doing this computation on each patch. And then we get something from the old data warehouse. So we're getting our phi at our old time step, which is something we're going to need. And we're also allocating space for our new phi that we're going to compute. So we have to allocate space in the data warehouse in order to do that. So this is kind of like the analogy, you can't just take a book off the street or from your own bookshelf and just stick it in the library. You have to allocate space for it. Okay? So then, the actual computation is done here. This is this, three-dimensional Laplacian discretization. And you can see, we're using phis from neighboring cells. And so So when you look at the call to get our fee from our old data warehouse, you'll notice at the very end there's this ghost around nodes. So the framework provides you a way to request ghost nodes from the data warehouse. And if we look at the schedule time advance method, we can see we had to request that from the data warehouse. So this isn't a coincidence that we can just grab those ghost cells. The only reason we can do that is because we told the scheduler that this task requires that data, and it requires ghost cells in a layer of one ghost zone. Okay, so we calculate our new fee, we calculate our residual, and then we put that residual variable into our new data warehouse. Okay. And that's all there is to it. So this example is a really simple example. And technically it's not actually integrating a PDE in time. It's just using each time step as a nonlinear iteration. And so the time step doesn't come into play here. But you can kind of extrapolate. If we were solving something in time, we could do something similar. Okay. So just to reiterate, we saw this schedule time advance. So that task specified that this computational task is going to require fee. And then there was a corresponding call to get from the old data warehouse. There was also this specification that the task computes fee, and then there was a corresponding call to allocate and put in the data warehouse. And then finally, the scheduler specified that the task computes a residual, and so there was a call to put that residual in the new data warehouse. Okay. Okay, so I'm just going to show you the input file. So in order to actually run this, we have to give sus some input file. So this input file is located at this location, this Uinta, wherever you checked out Uinta, source, standalone, inputs, and examples. And there's a Poisson1.ups, and UPS stands for Uinta problem specification. So you can see there's a couple of things in here. There's some information about the time stepping, how many time steps we want to run for, the total amount of time we want to run for. There's this information for the data archiver, which is basically the manager for the data warehouse. So we specify where we want to save this data to and what variables we want to save. So when we create a variable label, we have to give it some name. And then we come here and we write a save label, and then we give that name, the name of whatever variable label we want to save. And then here's the Poisson block. So this Poisson block is specific to this Poisson solver component. If we had a component named, so if we're looking at the arches component, then we're going to have an XML block that's for arches. And if we're looking at the ice component, then we're going to have a block that says, ice. And if we're looking at the NPM component, we'll have an NPM block, and so on. And then there's also this grid. So we have to specify the grid, and we have to specify boundary conditions. And here's where we specify our domain size and the number of cells we want in each direction, and also how many patches we want. Okay. And that's the end of the problem specification, so it's pretty simple.
Patches are like processes.
Yes. So if we want to run this, then we can give our path to sus. So I'm going to give path to my sus. And then we'll give it the path to this UPS file. Oops. And we'll see it starts to run. And at each time step, it's printing, what time step it's on, how much time has elapsed, how much memory has been used, and the residual. So it gives us all this information. Okay. And the reason that it's printing the residual twice is because it's performing this computation on 2 processors, or in this case, 2 cores. Okay. So if I look at the patches, I specified there's going to be 2 patches. And so that's why it was printing the residual twice. If I specified 1 patch, then it would only print the residual once. Okay. Oops. This should be Poisson 2. So there's a couple of other examples available in that examples directory. There's a Poisson 2 example, which demonstrates the use of sub-schedulers. So any particular task can create a scheduler of its own. And that scheduler will also have a sub-data warehouse. And so any particular, any given task can have its own scheduler and its own iterations. And so this is great for something like a nonlinear iterating, solution algorithm. So let's say we're solving a PDE in time, and our right-hand side has a Laplacian on it. Then what we want to do is we want to iterate on the right-hand side, but we also want to advance the solution in time. So we can use these sub-schedulers to iterate on something nonlinear within a given time step. There's also a heat equation example, which isn't much different than the Poisson example. It's just solving a heat equation. So it's a little bit more, I guess, applicable. There's also a solver test. So this is one of the nice features of this framework is you can interface with a generic solver interface, and that solver interface can then call different solvers. So for example, there's a linear solver package called Hyper. And so what you can do is, if you have a stencil, let's say you're at grid cell that's here, so your stencil looks something like, say it looks like this. So you require one neighbor cell in each direction. So this is going to translate into a matrix that looks something like this. It's going to be a tridiagonal or a multi-diagonal system. And so you have some stencil, and then that stencil translates into a matrix. So this solver interface can use something like Hyper to solve this linear system, which is really nice because Hyper is a scalable linear solver package. So Hyper can scale to thousands of processors. And so you don't get bogged down in your simulation trying to solve matrix systems like this because you have to code your own linear solver package. Okay. So the solver test 1 example demonstrates an example of how to use that. And just to sort of point you to the interface is located at CCA ports solver interface, and then that calls solvers that are located at CCA components solvers. And there's a couple of different solvers there, but the main one that's useful is this Hyper solver. Okay, and then there's another example on how to solve that solves the Burger's equation, and just using a forward Euler scheme. So there's a couple of useful examples there. You can kind of browse through those examples and get a feel for how the framework works. And just to sort of point you to more information, there's the user's guide and the installation guide. Those are located in Uinta and Doc. And those user guides and installation guides, the intention is to have those contain any information that's applicable to all users of Uinta, no matter what computer they're running on, no matter where they're running. So it's sort of general information related to Uinta that can be used by anybody. The Uinta wiki, on the other hand, contains non-general information. So if there's a cluster that you're running on and you have a configure line that's specific for that cluster, or if there's something you need to do to make Uinta run on that particular cluster, something you have to do, then that's where that information goes. Okay. There's also Uinta Doxygen. So there's a couple of classes that have Doxygen comments in them. Does anybody know what Doxygen is? Anybody who doesn't? Okay. I was going to say, nobody can answer no to both. Okay, so Doxygen is a way of creating documentation from the code itself. So the idea behind Doxygen is to eliminate things like this user's guide and eliminate things like this wiki, and basically put all the useful information inside the code using special comment blocks. And then Doxygen is just a third-party program. So you run Doxygen, you point it to your code, and it will generate documentation for you. So let me show you what that looks like, because this is a really cool program. Okay, so we've got some tabs up here, some namespaces, some classes, some files. So it's not just like a user's guide that you sit down and read. This provides you with a very interactive view of what classes there are, what classes are related to other classes. So for example, when I click on classes, I get a list of all the different classes in Uinta. So I'll go to Uinta the Arches class, and I get information about this. Okay, so this Arches class interfaces with a Uinta parallel component, and it interfaces with the simulation interface, and that in turn is part of the Uinta parallel port, and so on. So you get this sort of hierarchical view of what the class does. It also gives you information about types that are defined in that class. So here's some enums. It gives you information about the public members of that class. So here's some booleans. Here's the constructor for it. So even if there's no special comment blocks, this is still really useful information. Okay. If I keep scrolling down, I see, okay, here's the private members. Here's the private attributes. Detailed description, so I can look at the actual file. And here's the actual Arches file. So it's a really neat tool for creating documentation. And so all the classes that are, anything in that Uinta tree that's a class is going to be here in this list. So let me find one that's actually got some useful so using these special comment blocks, I can add information to this. So for example, there's a class defined here, and so here's a short little description. And that short description comes from the actual code itself. There's a special comment block that says transport equation class for a DQ mum scalar. And so Doxygen takes that special comment and it puts it there, so you can see, okay, this is a brief description of this class. Here's a more detailed description. Here's the person who wrote it. Here's the date they wrote it. So it's really nice to have this sort of information. Here's the members of that. Oops. Yeah. So there's the actual file, and so on. So Doxygen is just a really nice way of getting a better perspective on the code. Just a couple more things. There's a homebrew email list. So this is an email list for Uinta developers. So if you can't find something, then you can always ask somebody on the developers list. And if you can't find something in the documentation, you should also email John Schmidt, because he's the person in charge of documentation. So he wanted me to tell everyone that if you can't find something in the documentation, email him. Okay, so a final word on how you can contribute. So I'm going to be honest, the documentation for Uinta sucks. The fact that there's a lot of different places where there's documentation, and it's just kind of scattered, and it is difficult to find what you're looking for. And a lot of the developers who know this stuff well enough, they don't care enough to contribute because they already know how to use it. The general attitude toward new users of Uinta has been, sit down with someone who knows it for 2 or 3 months until you get used to it, which is a terrible way of learning software. So it's really up to us, the users, to improve the documentation, because the developers aren't going to. So don't be afraid to contribute to the documentation. If you figure out how a class works, then add some comments in that source code file, or add something to the wiki, or if you find something that's wrong in the installation guide, then fix it. Don't be afraid to contribute, because nobody else is going to. If the users don't, then nobody else will. Okay, that kind of wraps up part 1. So I'll just take a quick break, and then maybe 15-minute break, and then I'll start on part 2, which is specifically arches, the arches component.